Hello, and welcome to Chapter 4, where we're going to be balancing some equations, talking about different types of equations, and then doing that dirty word in chemistry called stoichiometry that I'm hoping by the end of this will not be that bad of a problem. All right, so let's get started here by looking at balancing equations. All right, by balancing an equation, we have to make sure that we have an equal number of each atom on both the reactant and product side of our chemical equation. Okay, and so when we write our chemical equations, we're going to have things on the left-hand side that are called our reactants, and we're going to have things on the right-hand side of an arrow that are going to be our products, and they all have to balance each other out. So if I've got an A over here on my reactant side, I have to have one A over there on my product side as well, right? And that's because of the law of conservation of mass. Right? Mass can't be created or destroyed during a chemical reaction. So if you start with an A, you got to end with an A. And so we're going to see that here as we balance an equation on our next slide. So we can balance equations by changing the coefficients of things. The coefficients are the numbers out in front. The coefficients must be whole numbers. Okay, we're going to see that come into play on this example here in just a minute. All right, and you cannot change the subscripts. So I could have, say, like water here, right? And you could, when you're balancing it, like in our example there, like I could change the coefficient out in front to like a 2. Cool, right? I can do that, but you cannot change a subscript of water. Say I can't have it be H2O2 to try to balance this thing because now that becomes hydrogen peroxide. All right, and that's a totally different compound, so we can't do that. Okay, so to balance an equation, what I like to do is I like to write out everything that's on all of the different elements that I have on both the reactant and product side. Okay, so I'm going to have my reactants and my products, and then down the middle, I'm going to write each one of the elements. So I got carbon, hydrogens, and oxygens. Okay, so now I'm going to start counting things up. So on my reactant side, my carbons, right, the only place I see carbon is in C2H6. And so there's 2 carbons, and the coefficient's 1 out in front, so there's 2 carbons. And then on the product side, there's a carbon in that carbon dioxide. There's only 1 there. Now we're going to count up my hydrogens. I've got 6 hydrogens there in the C2H6, so there's a 6. And then on my product side, there's 2 from the water. And then I'm leaving my oxygen for last, and I'm going to show you why here in just a second. But my oxygens, I've got 2 oxygens there as my reactants, and I've got 3 as products. So let's start balancing the carbon. Okay, so I'm going to do that by putting a 2 out in front here as a coefficient. That's the only thing I can change are coefficients. When I put that 2 out there, right, I do change that. I balance my carbons. I have 2 carbons. But I also change those number of oxygens, notice, because now I have 2 carbon dioxide, so I actually have 4 oxygens from the carbon dioxide plus 1 more from the water. So that's 5 oxygens over there. All right, now let's balance my hydrogens. Okay, well, I've got 6 hydrogens as reactants, and I have 2 as products, so what if I put a 3 in there? All right, great. That changes those number of hydrogens to 6, but it also changes my oxygens. I have 3 from the different waters, and I have 4 more from the carbon dioxide, so I now have a grand total of 7. Here's where we've got an issue. Okay, I have an issue because I have an even number of oxygens on the left-hand side and an odd number on the right-hand side. But I can only really change the coefficient and the number of oxygens, the O2 there, in order to really balance this. So I'm going to do a trick, and I'm going to put in a fraction. And you can say, wait, you just said that it has to be whole numbers. That's okay, we're going to get to that. We're going to try to balance this. How can I balance this is by putting in the fraction of 7 halves of an oxygen there. Because 7 halves times 2 is 7. So this becomes balanced. All right. But I can't have a fraction. So what I'm going to do is I'm going to multiply all of my coefficients by 2. All right, and so when I do that, I get this. And now we can double check everybody. So I've got my carbons. I've got 4 carbons on the reactant side. 2 times 2 is 4. And I've got 4 carbons, because I've got 4 and there's times 1, so 4 carbons on the product side. Then my hydrogens. I have 2 times 6 is 12. All right, and then 6 times 2 is 12. And then my oxygens. 7 times 2 is 14. And then 6 times 1, there's 6 oxygens. And 4 times 2 is 8 oxygens, is 14 oxygens. It is balanced. All right, that's how we balance an equation there. That one's more difficult than the ones you'll usually see, but the same process, plays out for all of them. Next, we're going to talk about our different types of chemical reactions. Oh, wait, no, first we're going to talk about some other information that we might need in there. Okay, we might need to include the physical states of things. So we might have something like, say, calcium carbonate, and we might need to include that that's a solid, right? We put that in parentheses after whatever it is. And then we might need to include that we have calcium oxide as a solid, and it produced also carbon dioxide, which is a gas. Those states, those physical states of the matter are very important, and so they'll usually be in our balanced chemical equations as well. All right, so gases, liquid, solids, and aqueous species. Also, it says that there could be other special conditions. Now, this doesn't come up very often in Chem 1, but you might run across this, so I'm going to put it in. Right, we might see something like this where I have that symbol delta above this. All right, this means that heat was needed for the chemical reaction to take place. All right, now you might also see things like, you might see like an H nu where there's like, which we haven't really talked about, but you might see like this, where there might be light is needed for the reaction to take place. So if there's other things, we throw them above the arrows. So you might see those as you kind of working through problems. Just if you see it, don't freak out. All right, now we are going to classify our chemical reactions, right? And so there's 3 different types of chemical reactions that we're going to be interested in. First off, we're going to have precipitation reactions. Okay, so it says precipitation reactions where we have aqueous solutions are producing at least one solid. Okay, so we might have something like silver nitrate, and it's aqueous, and it's reacting with aqueous sodium chloride to produce a solid silver chloride and NaNO3 sodium nitrate aqueous. So we've got a couple of aqueous things, right? And notice, boom, you've got a solid. That is a precipitation reaction. So when you see something like that, ding, 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 if it asks you what type of reaction, that's a precipitation reaction. All right, acid-base reactions, right? Well, they are going to, right, have an acid and a base reacting together. And we're going to talk more about how to spot acids and bases here in a little bit, but acids, they start with an H. All right, so unless it's water or hydrogen peroxide, if you see a compound that starts with an H, in your brain you should think, ding, 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 that is an acid. So here I have hydrochloric acid, HCl. I'm going to react it with a base, sodium hydroxide. All right, many of these have an OH. Now we'll see some other ones as well, but if, like I've got here, sodium hydroxide, if I see that OH, ding, 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 there's a base. This is going to produce water. So acid-base reactions produce water and a salt. Okay, and a salt is a fancy term for a metal and a non-metal. All right, so that are basically usually from groups 1 and 2 with something from group 17. So here I've got a metal from group 1, sodium, and something from group 17, chlorine there. So it produces like an aqueous salt there. All right, and then we've got redox reactions. Those are the toughest ones to spot. So if it's not a precipitation, it's not an acid base, then just write down that it's a redox reaction. Redox reactions is where we have a transfer of electrons. So again, we'll see more on these soon. All right, but here I might have something like zinc is reacting with copper sulfate to produce zinc sulfate and solid copper. Okay, how do I know that there is a transfer of electrons here? Well, whenever I have a neutral, whenever I've got a neutral atom like zinc there, right, it has like a charge of 0. All right, but over here, when I've got this zinc sulfate, sulfate has a charge, by the way, of -2. And so for the whole thing to be neutral, my zinc has to have a charge of +2. So my electrons were transferred there, right? It started as being 0, and it's now +2. So it must have lost a couple of electrons, right? It lost a couple of negatively charged things. Same thing in this case. Our copper here is +2, and over here it became 0. All right, so the electrons have to go somewhere. They're being transferred around. They can't just go off into space. All right, so in this case, our copper like added a couple of electrons to have its charge go down. All right, so let's look at acid bases. All right, so acids are always going to start with a hydrogen unless you see water and hydrogen peroxide. Right, and then bases are generally going to have an OH, or you're going to see a compound where you've got NH2 or NH3 in it. Right, and I've got a couple of examples of those out here. Those are some like weak bases. Strong bases have OHs. Right, here I've got a list of 7 strong acids. Okay, all other acids are weak. Okay, so if it's an acid and it's not on this list, it is a weak acid. Okay, so that's going to be helpful at some points along the way. So again, you don't have to memorize tables and stuff like that, but have fast access to these sorts of things as you are working problems, or especially whenever you're doing exams. So you don't have to waste a lot of time being like, okay, is that a strong acid or a weak acid? That, you know, as you need to do other parts of the problem, you'll be able to grab that and use it really relatively quickly. All right, now redox reactions, right? Again, right, is probably the worst thing. Is one, you just got to be able to recognize things as tough enough, and then two, it's got all sorts of weird verbiage along the way. Okay, so it says oxidation is a loss of electrons, and reduction is a gain of electrons. That makes no sense until you start thinking about it. Reduction is a gain of electrons. So what I mean by that is that when you gain electrons, you're gaining negatively charged things, and so your charge is actually going down, or your charge is being reduced. Right, an easy way of thinking about this one, right, is like oxidation is a loss, reduction is a gain. So most people think of this as oil rig. I use that mnemonic all the time to help myself think about it. Then it gets even more confusing. A reducing agent is what was oxidized, and an oxidizing agent is what was reduced. Oh my goodness, these are all sorts of really confusing things. All of these things, at least, must be reactants. Oh, I said that right there, didn't I? I didn't even notice that I said it right there. But they all have to be reactants, so if I do ask you, what is a reducing agent, or what species was oxidized, or something like that, at least narrow it down to the things that are reactants and get rid of the things that are products, because those can't be possible answers. All right, so when we are going to deal with this, right, what we have with our redox reactions is that our oxidation numbers, or the charges on species, are changing. So let's look at some rules of oxidation numbers. Right, as we kind of did with a really quick thing a couple of slides ago, was we saw that elements are zero. Right, so remember I had like zinc had the charge of 0, its oxidation number is 0 is what I meant by that. Or copper, right, was 0. Right? Monatomic ions are the same as their charge. So magnesium cation is +2, right? Or the chloride anion is -1, right? So those are really easy to spot if they're just written out there. Right? Other oxidation numbers. Hydrogen's kind of tough. Hydrogen is +1 usually when it's with a nonmetal and -1 when it's with a metal. All right, for our purposes, we're going to assume that oxygen is -2. Oxygen loves to be -2, so we're going to have it being -2, although there are exceptions to this. For us in our class, it's just always going to be -2 for any of the problems that we have. And then it says that the sum of the oxidation numbers is the sum of the molecule or the ion. Okay, so what I mean by that is like here, right, we have this whole ion is -3. Or sorry, -2. I can't even look at that number and pick it out. Okay, so I've got 3 oxygens that are each -2. So that's -6. So the sulfur for this then, right, in order for the thing to overall be -2, right, the sulfur has to be +4. Right, because +4 and -6 is -2. So what we can do is we can infer from the other elements, all right, what the species is that we don't know. So for our next one, right, our K2CrO4, all right, so I have this thing, the whole thing overall is 0. So overall it has to sum up to be 0. All right, so, right, if I wanted to do this, let's say that our potassium is +1 because it's a group 1 cation, if we remember that from a couple chapters ago. So +1, and there are 2 of them. All right, and then I have oxygen. All oxygen is -2, and there are 4 of them. So that is -8. So right now I have -6. The whole thing has to be 0. So the CR has to be +6 in this species in order for this to sum up to being 0. All right, let's move over now to stoichiometry. It's a big change, I get it, okay, but we're going to build upon some of the stuff that we did. So stoichiometry really is like that dirty word of chemistry, and so let's hopefully make it as easy as possible. So I like to think about stoichiometry not in terms of chemistry right off the bat, but more of us thinking about like us, like, you know, being bakers in the kitchen. Okay, so it says stoichiometry is the quantitative relationship between amounts of reactants and products. Okay, really, all we're doing is we're doing recipes. And I guarantee that you have probably done this on your own without even thinking about it. Okay, so notice over here I've got a picture of some Nestle Original Toll House cookies. Okay, and so in order for us to make a batch of Toll House cookies, right, it's got the ingredients listed out right there. Okay, but what if you want a double batch of cookies? How many eggs would you need? Okay, well, I mean, come on. Right? If you need 2 eggs to make one batch, I guarantee all of you right now are like 4, right? Without even doing the stoichiometry or the chemistry behind it. Right? You need 4 eggs to double it. You're just going to double everything that's present there. If you wanted to make a half a batch of cookies, you need 1 egg. Right? You have done this. That's all we're going to be doing with stoichiometry when it comes to chemistry. But instead of it like kind of being a listed out like list of ingredients like this, we're going to have a balanced equation that we're going to be using. Same idea though. So our balanced equation then becomes our recipe. So here I've got 2 hydrogens plus an oxygen producing 2 H2Os. Right? And so we need 2 hydrogens to make 2 waters. Or I need 1 oxygen to produce 2 waters. Right? Or how many oxygens do you need to make 4 waters? I bet you're thinking, you know this, it's 2 oxygens is the answer, right? That's all stoichiometry is. Now, it's a little bit more complicated because like we have to like write these things out, but that's really what you're doing. So there's mathematical relationships for all of these things. And if we write out all the mathematical relationships, then we can use them to be able to convert from one species to another. So, right, there are 2 moles of hydrogens for every 2 moles of water, right? Or we can write that as the inverse. 2 moles of water for every 2 moles of hydrogen. All right, and also 1 mole of oxygen per 2 moles of water, or 2 moles of water per 1 mole of oxygen. And there also doesn't have to be reactants and products. They could both be the reactants. So it could be 2 moles of hydrogen per 1 mole of oxygen, or 1 mole of oxygen per 2 moles of hydrogen. All right, now let's see what I did there. How many moles of oxygen to make 4 moles of water? So what I really did there, right, is I used this relationship here, that 1 mole of oxygen per 2 moles of water. 4 divided by 2, right? That's how I got that. Now, we did it in our heads just because we know it, but like here, right, we want to make sure that we can actually solve these because, you know, they will get more complicated than that. They won't all be like these perfect little, like, you know, values. But like right there, we did it in our heads, but here we showed that we can do it mathematically as well. That's all stoichiometry is going to be. So let's do a stoichiometry problem here, right? What if we start with 1.2 moles of magnesium chloride? How many moles of sodium chloride could we produce by this reaction? Okay, now it says assume you have plenty of sodium hydroxide, right? Meaning, right, like if you've got a recipe, what I'm saying is that, like, you know, we've got enough of all the other ingredients, and we only want to focus on the one ingredient, the magnesium chloride, that we're interested in. Okay, so, right, what I want to do is I want to say, all right, I have 1 mole of magnesium chloride is equal to 2 moles of sodium chloride. All right, and then I can write that as a ratio. So I have 1.2 moles of my magnesium chloride. All right, now, Right? I want to get rid of the magnesium chloride and I want to get sodium chloride. So I'm going to put the magnesium chloride on the bottom so that we cancel it out. Right? Boom, canceled out. And I'm going to put the sodium chloride on the top so that we get that. And so we get this to be 2.4 moles of sodium chloride. Right? That's all we're going to do for our stoichiometry stuff. All right. Next off, right, is I went from moles of one species to moles of somebody else. Okay, but what if I want to go from grams of something to grams of something else? Okay, well, the problem is that I can't do it directly. Right? I can't go from grams of A directly to grams of B. Okay, but what we can do is we can do a workaround. And I can convert to moles of something, and then moles of something else. All right, and that's what we're going to do here, right? And so it becomes a little more complicated, but all we're doing is building upon the steps that we've already done in the past. So it says 1 mass of sodium hydroxide, NaOH, would be required to produce 16 grams of magnesium hydroxide. Okay, so I'm going to start with, I have 16 grams of the magnesium hydroxide was the given thing in our problem. Okay, we're going to try to find a way to get over here to grams of sodium hydroxide, because that's what it's asking about. Again, I can't go directly there, so I'm going to go from my grams of magnesium hydroxide to moles of magnesium hydroxide. Okay, this grams to moles is by using that molar mass that we did back in like chapter 2, I believe. Forget chapters. Okay, but that is 1 mole of magnesium hydroxide per whatever it weighs. Okay, so we figure out the mass of magnesium plus the mass of 2 oxygens and the mass of 2 hydrogens. All right, and so, right, we've got our moles of magnesium hydroxide. Now we're going to go to the moles of our sodium hydroxide. And we're going to get rid of the moles of our magnesium hydroxide. Okay, so our moles of our sodium hydroxide are going to come from, oops, our balanced chemical equation. So that's that 2 right there. We're going to plug right in here. And then for the moles of our magnesium hydroxide, why is that black? Then we'll get it. Okay. There's a 1 right there. Right? I'm going to plug that 1 in there. Okay, now finally I can go to the grams. So again, this is using the molar mass. The steps from moles to moles is called using the mole ratio. That's using those coefficients that are in there. All right, so now I want to get to grams of NaOH. So I'm going to have to figure out what it weighs. So the mass of sodium plus the mass of a oxygen plus the mass of a hydrogen. So we get 40.0 grams of NaOH per 1 mole of NaOH. Okay, so multiply all the things on top, divided by all of the species on the bottom, and we're going to end up with, we needed 22 grams of sodium hydroxide to produce 16 grams of magnesium hydroxide. All right, so we just added a new step in there along the way. All right, next up we're going to talk about reaction yields in things. This will be our last little section here in chapter 4. So, right, reaction yields depend on the amount of our reactants that are present. So again, let's go back to our Toll House cookies, right? And so let's say that you have all the ingredients listed, right? You're going through, you've got plenty of flour, you got your baking soda, you got your salt and everything, and then you get there and you notice, oh man, I only have one egg. Okay, well, that egg is going to limit the amount of cookies that you can make, right? You can't make the full batch of cookies because you only have one egg. So if you only got one egg, you can only make a half a batch of cookies. Same thing happens with our chemical equations. Depending on how much of our reactants we have, that'll limit what our reaction could possibly be. Okay, so how are we going to determine our limiting reactant? All right, well, I'm going to make some hot dogs. All right, so determining our limiting reactant, right, how many products can we have from our starting materials? Okay, the age-old question, right? Why, when you go to the grocery store, do you buy packs of hot dog buns where you got 8 buns, and you go and you get the hot dogs, and there's 10 hot dogs in a package of hot dogs? That makes no sense. So, right, if you've got a package of hot dogs and you've got a package of buns, right, you can only make, right, 8 dogs and buns combined, right? And so, in this case, 8 buns, 10 dogs, right? You would make 8 buns and dogs. You would have 2 dogs left over, right? And the buns are limiting, right? They limited how many buns and hot dogs we could put together, right? We ran out of buns. We still had hot dogs left over, right? Those are in excess. Okay, so for a chemical reaction, same sort of an idea here, right? I've got my 2 hydrogens and my oxygen producing our 2 waters again. Okay, what if I had 8 moles of hydrogen and 8 moles of oxygen? This is a little bit trickier because, like, it's not like just counting up dogs and buns and being able to, like, kind of figure that out, right? This is where we got to be able to do the math on this. So what we're going to do is we're going to find out how much we can produce, how much of the water we can produce from each one of them individually. The one that produces the least amount is limiting. Just like with our hot dogs, right? The one that produces the least amount are buns that limited our reaction. So I have, right, 8 moles. All right, we're going to start with 8 moles of hydrogen. And I want to find the moles of water. Okay, so there are 2 moles of water. Right, again, that 2 comes from the coefficient in front of water. For every 2 moles of hydrogen. Okay, so if I had 8 moles of water, I could theoretically produce 8 moles of water. if I had 8 moles of oxygen, all right, there's 2 moles, it's going to produce 2 moles of water for every 1 mole of oxygen, right? There's an implied 1 out in front of that oxygen there. Okay, we could theoretically produce 16 moles of water. All right, that is the smaller value. It is the limiting reactant. It is going to run out, okay, before the oxygen runs out. So, this one's bigger. It's an excess. There will be some left over. Once our reaction takes place, right? So we're going to make that's the amount that we could make. It's only the amount from the limiting. We're not going to be able to make that 16 moles. Okay, so this then is going to lead us to our last slide. We finally have made it to the last one, which is theoretical and actual yields. So that limiting reactant tells us theoretically how much we could make. Right? So from our previous example, right, it was like the 8 moles of water theoretically made. All right, now I said that's how much would be made, but really that's theoretically how much could be made because, right, that's the maximum amount. You're likely not going to be able to make the maximum amount. Okay, like let's say that I was going to make those hot dogs and I got my hot dogs and my buns that are out there, right? Well, and I walk away to go and, set the table with some mustard and ketchup and relish and put out all the fixing and stuff like that. And I turn my back and my jerk of a dog counter surfs and eats one of the hot dogs. Well, that's going to change, right, how much we can possibly make. Actually, it's going to change it if he eats like one of the buns. But like, so something along the line happens. And that happens when we talk about chemistry too. Right? What's happening like with chemistry though is like you've got like things like maybe in beakers or maybe in test tubes and you're going to mix them together. Well, if you've got a liquid in a glass, and you pour it out and then you look at it, right? There's always going to be like a little bit that's left over on the sides, but you can never quite get everything out. And so that's going to kind of mess with the actual amount that you make because maybe, you don't get them all mixed together. Or maybe you've got those things that are floating around in solution, and in order for them to react, they have to like come into contact with each other. And maybe they're floating around, they just never do come into contact with each other, and so the reaction just can't take place. So the actual yield is you're always going to produce something smaller than what you theoretically think that you're going to be able to come and make. Right? So you can calculate the percent yield, right, by figuring this as being the actual amount divided by the theoretical amount times 100. So after your experiment, you find you only produced 7.6 moles of water. What is its theoretical right? Yield. Right? Well, the actual amount is 7.6 moles. You theoretically thought you could have made 8. It was the lesser of those two, not the 16 and the 8, times 100. All right, so, right, you actually produced only 95% of what you theoretically thought you could. All right, another chapter down. I will see you next time for chapter 5.